This is the second video of a two-part series which provides an example of how to use the Mile High Flood District's Detention Basin Design Workbook. My name is Derek Rapp, and in the Part 1 video, I explained how to use the Basin worksheet to develop a stage area volume relationship for a full spectrum extended detention basin. In this video, I will continue the same example and walk through how to use the outlet structure worksheet to develop a stage discharge relationship that controls the release rate from the basin to pre-development levels. I have opened the same workbook from part 1 of this example and switched to the outlet structure worksheet. When opening this worksheet, the estimated stage and storage volume for each zone selected on the basin sheet will automatically be carried over and shown here. It should be noted that these are only estimates based on the empirical detention volume equations. The actual stage and storage volumes required will be calculated on this worksheet by routing the CUHP-generated inflow hydrographs through the outlet structure using the modified pulse routing method. If we scroll over to the right, we can see the CUHP inflow hydrographs that were generated by clicking the Run CUHP button on the Basin worksheet. You may notice that the WQCV and EURV columns are all zeros. This is because they are evaluated using the brim full capacity of the capture volume instead of using an inflow hydrograph. The hydrographs in this table can be overridden by the user if the upstream watershed is more complex than a single catchment or includes upstream detention facilities. For example, EPA swim results for multiple subcatchments routed through a conveyance network could be pasted into this table. In this example, we are going to stick with the CUHP-generated inflow hydrographs. The first step on this worksheet is to select the outlet type you would like to use for each zone. In this example, we are going to use an orifice plate to control the release rate for the water quality capture volume and the excess urban runoff volume in zones 1 and 2. As you can see for Zone 1, only options relevant to the BMP type selected will be included in the pull-down list. When we select orifice plate, the program will automatically set several default values within the worksheet. For example, the under drain section is now shown as not applicable, and the depth at the top of the orifice plate is set equal to the estimated Zone 1 stage. Then, when we select orifice plate for Zone 2, the depth at the top of the orifice plate is updated to equal the estimated Zone 2 stage. For the 100-year design storm, we will use an overflow weir and drop box with an outlet pipe and flow restrictor plate to control the release rate of Zone 3. Now that we have selected the outlet type for each zone, we need to provide the required inputs for each applicable section. In the orifice plate section, the program has already set the default values for the lowest orifice at 0 and the top of the plate at the estimated stage for Zone 2. The program also assumes a default of 3 orifice openings with a vertical spacing between them set equal to 1/3 of the plate depth. If desired, any or all of these default inputs can be overridden. If the orifice openings are evenly spaced and the same size, you can just enter the values here, and the table below will update. However, if the orifice openings are different sizes or spaced unevenly, you can enter the specific values directly in the table below. In this example, we are going to use the default stage values and default vertical spacing of the 3 orifice openings. We are also going to let the program determine the orifice area for each row necessary to match the desired water quality capture volume drain time. When we click on this button, the program will iteratively solve for the orifice area that drains the water quality capture volume out over a 40-hour period. It may take a little while for the program to find a valid solution. In this example, an orifice area of 2 square inches per row was calculated. Now we can move down to the overflow weir and outlet pipe sections. The overflow weir front edge height is already populated with a default value equal to the stage at the top of the EURV in Zone 2. Next, we need to define the overflow weir and drop structure geometry. In this example, we will start with a front edge length of 4 feet, a grate slope of 4:1, and a horizontal side length of 4 feet. We will estimate the grate open area at 70% and initially size the outlet structure assuming no debris clogging. Later, we will come back and reevaluate the design by checking the grate under clog conditions. Off to the right, you can see a few interim calculations based on the overflow weir and grate values entered. For example, the height of the grate at the back of the drop box is 1 foot higher than the front edge based on the slope of 4:1 and the side length of 4 feet. Now we can move on to the outlet pipe with flow restrictor plate below. First, we need to provide the depth to the invert of the outlet pipe. In this example, we will place the pipe 2.5 feet below the lowest water quality orifice invert, which is the recommended depth of the micropool. At this point, we can let the program fill out the rest of the required inputs and generate results simply by clicking on this button. The program will first start by determining the outlet pipe diameter and restrictor plate height necessary to control the 100-year release rates to 90% of the pre-development release rate. Next, the program will check the overflow weir and grate geometry to make sure that it does not unintentionally control the 100-year release rate. If it does, the program will ask the user if they would like to change the weir front edge length. Finally, the program will determine an emergency spillway invert stage that is above the maximum 100-year ponding depth and ask the user to provide an invert stage equal to or greater than the calculated value. We will just use the calculated value of 6.1 feet. It will then size the length of the emergency spillway to pass the developed 100-year design storm runoff in case the outlet structure becomes clogged. Once the outlet sizing routine is finished, the program will automatically generate a staged discharge relationship for the outlet structure and then route the CUHP inflow hydrographs through the basin to generate discharge hydrographs. At this point, the program has finished, but it has determined that the 5-year storm is not draining out within 72 hours, which violates the Colorado revised statutes related to water rights. To address this issue, we can modify the top opening on the orifice plate within Zone 2. But first, let's take a look at these results. We can see that the program solved for an outlet pipe diameter of 18 inches with a restrictor plate height about 13.5 inches above the invert. We can also see that the spillway invert stage is just over 6 feet and the spillway crest length is around 17 feet. Now let's scroll down and look at the routed hydrograph results summary table. The complete calculation tables are hidden below and can be viewed by clicking these buttons. You may notice a few cells in this table are highlighted pink. The highlighted cells indicate that either the input value is overridden by the user or that the results do not satisfy the recommended criteria. The first 7 rows in the table are based on inputs from the Basin worksheet and the CUHP generated hydrographs. The results include the rainfall depths, CUHP runoff volumes, and pre- and post-development peak flow rates. The remaining rows in the table show the results of the modified pulse routing method calculations. The peak discharge for each design storm is shown in this row. The ratio comparing the discharge to the pre-development level is shown here. You can see that the 100-year release rate is 90% of the pre-development rate. The next row identifies which element of the outlet structure is controlling the release rate for each design storm. In this example, the orifice plate controls the water quality capture volume 2-year and 5-year events. The overflow weir controls the EURV 10-year and 25-year events. And the outlet pipe restrictor plate controls the 50-year and 100-year events. Also, the emergency spillway conveys the 500-year event. These rows provide a check on the velocity through the overflow weir with grate to make sure they don't exceed 2 feet per second from a safety perspective. These rows show the drain time for each event. We can see that the water quality capture volume drains out in 40 hours. However, the 5-year event drain time appears to be just over the limit of 72 hours, and we will fix this in just a second. The last 3 rows show the actual routed results for stage area and volume, as opposed to the estimated volumes determined on the Basin worksheet using empirical equations. Alright, now we can modify the orifice plate to decrease the 5-year drain time. We can see in this table that the water quality capture volume ponding depth is approximately 2.6 feet. Now, if we scroll back up to the orifice plate section, we see that the row 3 orifice stage is above 3 feet and would not have an impact on the water quality capture volume drain time. Therefore, we can increase the orifice area in this row, which will decrease the 5-year drain time. I will start by doubling the area to 4 square inches, and the program will automatically update all of the results. If I go back and check the results, we can see that the 5-year drain time is no longer violating the statutes. We can also check and see that the 100-year design storm is released at 90% of pre-development levels. It also has a maximum ponding depth of 6 feet with a maximum storage volume of 2 acre-feet, consistent with the empirical equations on the Basin worksheet. Now we should check and see how the design would perform if the overflow weir grate became partially clogged. We can change the debris clogging to 50% and evaluate the impacts of the grate becoming clogged during a large storm event. Again, all of the results will update automatically. If we look at the 100-year event, you may notice that the emergency spillway is now controlling the release rate because the maximum ponding depth has exceeded the spillway invert. We can easily address this by raising the emergency spillway invert up slightly to 6.2 feet. Looking back at the results, we can see that this adjustment allows the outlet pipe to still control the 100-year release rate even when the grate is partially clogged. It is always good to look through the figures to the right to make sure the results look reasonable. The bottom figure shows the stage area volume discharge relationship. The figure in the middle shows the ponding depths over time for each event on a logarithmic scale. We can see that the water quality capture volume empties out in 40 hours, and the other events are between 60 and 80 hours. The top figure shows a comparison between the inflow hydrographs and discharge hydrographs. You can clearly see the flat top of the 100-year event, and you can also see how the 500-year event is conveyed through the emergency spillway. That concludes part 2 of this example. Be sure to check out the other instructional videos available.